Welcome back to another aerodynamics video. Today we're going to be diving into canards. What a canard is a forward lifting surface used in place of a conventional tailplane. Think about it like putting the tail in front of the wing near the nose of the aircraft, instead of behind the wing like you see on a normal plane. Unlike a tail, which typically provides negative lift to balance the pitching moments generated by the main wing, the canard generates positive lift. This changes the way the aircraft balances in pitch and shifts the aerodynamic center forward, which has implications for both stability and efficiency. The configuration has sporadically made appearances in various experimental designs throughout the history of aviation, and really got traction in the public eye through Rutan's Very Easy and Long Easy kit planes, which were designed in the 70s. The lifting canards on these planes are only about 15% or so of the total wing area, but carry anywhere from 25 to 33% of the total weight of the aircraft. This video will explore how canards work, why they're used in some aircraft, and why they're often avoided. We'll look at lifting and control canard configurations, we'll touch on three-plane configurations, we'll review the aerodynamic role of canards in trim and stability and the pitching moment contributions from each surface, and we'll discuss how stall characteristics are managed by design. We'll also cover the complex aerodynamic interaction effects between the two lifting surfaces, CG constraints, and we'll take a look at some FlowViz and CFD that will help us to explain why canards are difficult to implement successfully for net positive performance changes. Canards are a notoriously sensitive trade-off among several contrasting aerodynamic characteristics, and the design process is sensitive. I'm going to try and structure this video in a manner that's beneficial to you, the viewer, the student, the designer, the engineer, whatever you are, and your understanding so that you can apply these principles and theories correctly. It always helps me to learn the why before the how, and I think that it'll help you too. With that being said, the how is still incredibly important because after all, this is the way you implement. It's just important to understand why the designs and features that you're implementing do what they do, and sometimes that requires some hard thinking and studying, and that's okay. If these things were easy, everyone could do them, right? Alright, a couple of interesting facts before we get into it. The name Canard originated from the Santos Dumont 14, a Pioneer-era biplane built in 1906 that resembled a duck with its neck forward in flight, and the French word for duck is canard. Also, the Wright Flyer was a canard configuration. Besides one of the coolest aircraft of all time, the XB-70 Valkyrie, and Rutan's Starship design, here are a few cool canard planes that I can bet you've never seen before. A 1940s experimental fighter dubbed the XP-55 Ascender was a very unconventional design for the time. It never entered service, and the program was cancelled when testing revealed that its performance was inferior to that of conventional fighters, and it also didn't help that the first jet fighters were just getting operational. Because of the canard up front instead of a tail in the back, and because of the pusher prop setup, the Ascender was also referred to as the Ass-ender. The much louder and much less efficient Soviet predecessor to the Concorde, the Tu-144 Charger was a supersonic passenger airliner featuring two small retractable surfaces near the nose called mustache canards, as well as a drooping nose. The mustache canards were equipped with double-slotted leading-edge slats and double-slotted trailing-edge flaps, so they could generate a huge amount of lift. The role of these was to increase lift at low speeds, and they would then retract back into the fuselage at high speeds. There is also a configuration known as a three-surface or three-plane aircraft, which involves both a foreplane or canard and a conventional tail simultaneously. I'd love to go into detail on these, but I just don't have the time in this video, so let me know if you want to see another on these layouts. Here's a few more cool canard concepts for you to check out if you feel so inclined. Okay, so what do canards do, and why would someone design an aircraft with these rather than a conventional tail layout? At the highest level, an engineer or designer can utilize a canard to either reduce the loading on the main wing, to increase stall safety, or to increase maneuverability. Now, there are two primary canard configurations: lifting canards, which act as a second wing and carry a portion of the total lift, and control canards, which mainly provide pitch control with minimal contribution to the overall lift. So unless otherwise noted, when I refer to canards in this video, I'm referring to lifting canards. On the topic of canards, you could also include tandem wings, but for the sake of time in this canard video, I'll skip over these. One interesting note that more relates to fighter maneuverability applications is that if the aircraft is statically unstable or closer to neutrally stable, the control canard can be completely unloaded, which would avoid the canard-induced drag because it's not generating lift. This gives efficiencies equivalent to tailless delta wings because in cruise, the canard is only generating parasitic drag. Of lifting and control canards, there are also long arm canards and close coupled canards. For this video, we'll be checking out primarily long arm canards, but close coupled canards, which tend to be lower drag configurations due to the influence of the parent wing on the canard, are super interesting, and here's a paper about those. Remember that everything in subsonic aerodynamics affects everything else, and just because we can think through the effect of the placement of one wing relative to another, that doesn't mean there's not more complex interactions going on. While long arm canards do provide greater moment arms and thus potentially higher pitch rates, this benefit is somewhat negated by the fact that close coupled canards can be positioned to produce a low pressure zone at the front of the wing, which has a similar effect. The tip vortices from noticeably long arm canards burst early due to the lack of the influence from the parent wing, and this means that long arm canards have no real influence on improving the main wing's lift beyond the increase in total wing size that it provides. This means that it does not reduce drag at high angles of attack as the close coupled canard does, and consequently the long arm canard configuration has a higher drag than even the standard tailless delta at high alphas. Zero lift drag is also more likely to be increased as long arm canards are harder to fit in the overall body area distribution, but if done well, the zero lift drag of the long arm canard can be less than that of close coupled canard configurations, and the cruise drag would also be less at subsonic speeds. So because the total instability of the aircraft using the long arm canard has to be greater than that of one using the close coupled canard for the maneuverability benefits we just mentioned to be realized, the long arm canards are inferior for maneuvering combat regardless of instability levels, and they're generally a better choice for bomber interceptors, supersonic bombers, and civilian aircraft than for air superiority. But even then, there's always an oddball exception like the Mirage Milan with its long arm canard with an insane amount of dihedral for some reason. Interestingly, if a canard is added in post as an existing aircraft performance improvement, the foreplane will add lift ahead of the CG, meaning that downward elevon will be required to trim properly, which then means that we're adding lift both ahead of and behind the CG, which further reduces the takeoff distance. Before jumping right into design tips, let's take a little bit of a closer look into stalls, because after all, the primary utilization of canards is to enhance the stall performance. So canards can be considered a stall-proofing device. Because the canard must stall before the main wing to prevent a deep stall entrance, at some high alpha you lose your forward lift, you lose your canard lift, and because your main wing is still lifting at some lift coefficient below its CL max, and it's not stalled yet, this ends up lowering the nose. For reference, in Burt Rutan's notes for the Very Easy and Long Easy designs, he says that a design approach is to use a canard airfoil whose lift curve peaks at a lower alpha than the wing, even though it has a higher CL max. And in practice, the canard stall alpha is about 15 degrees, while the main wing's airfoil stalls closer to 17 to 18. Realistically, you can still stall the wing of a canard plane with a high enough rotational momentum and pitch. And here, what we're talking about is a dynamic stall effect where the canard's lift coefficient would quickly increase beyond its CL max, but the canard would also experience a sharp and sudden deep stall development very soon after. Interestingly, you can still fly around with a stall canard. There's not really a danger in this because you're not stalling your main lifting wing, so you still have your lift and you can maintain altitude and maintain full roll control. The requirement for the canard to be the first wing to stall requires that the main wing never reaches its critical angle of attack. And because we can't hit this critical angle of attack with the main wing, and hence cannot hit the CL max of the main wing, we have to increase the wing area of the main wing to reach the same required lift without operating at too high of an angle of attack, all to avoid the deep stall without drastically increasing our stall speed due to the inability to induce the first pass design CL max of the main wing. Obviously, the designer has to get handy here and design in proper stall margins for both surfaces simultaneously and relative to each other. But if we can't really stall the main lifting wing and we're generating lift instead of downforce like we would with a normal tail, why isn't the canard a huge advantage? Well, I'll repeat this a couple times in the video to drive the point home, but the downwash from the canard affects the main wing's effective alpha, and this ultimately requires an even larger main wing to maintain that same lift. Because only the inboard portion of the main wing is affected by the canard downwash, the main wing span-wise lift distribution becomes suboptimal or non-elliptical, and therefore the overall main wing efficiency is also decreased. Even with the enhanced aircraft lift due to the lifting canard, the main wing may still need to be larger than expected for the added lift of the canard, and overall, drag-wise, we often end up near the same exact spot that we began at with a tail. But still, in cruise, the canards lift upwards, and this contrasts to the conventional tail producing downforce. In that regard, the canard concept is more efficient than conventional aircraft, but again, this ends up being offset primarily by the downwash of the canard. As always, stability is our most major concern in aerodynamic configuration design, and for lifting canards, there are two primary requirements for stability. Also, for the majority of this video, whenever I refer to stability, I'm referring to the pitching or the longitudinal stability. The first requirement for stability with the canard is going to be that the canard must stall before the main wing, like we've discussed. Let's say a gust of wind induces a nose-up pitching moment. If the canard doesn't stall first, it will keep lifting more and more and more through the high alpha, which is statically unstable and divergent. But if we design the canard to stall first, at some point during the nose-up rotation, it will lose its lift, and the main wing, which is still lifting, being behind the CG, will cause a nose-down restorative moment, which is statically stable. And for the second requirement, the main wing should reach its zero lift angle before the canard does. This time, consider the same plane with a gust that causes a nose-down pitch, so it's at a negative angle of attack. If the main wing keeps lifting while the canard is generating zero lift, the aircraft will continue to pitch down because of that lift being generated behind the CG, and this is not necessarily statically stable. If the main wing reaches zero lift before the canard does, that is, the canard is still lifting at some negative alpha while the main wing is not, then naturally the canard being ahead of the CG and still lifting means that the aircraft will begin to pitch back up out of the dive. Obviously, this is the stable design. Now that we know the absolute basic requirements for canard configurations to be flyable, what parameters specifically can we manipulate in our configuration or layout to fulfill these? Logically, the first thing we should look into is the airfoil selection. We said that we want the canard to stall before the main wing, so let's use an airfoil with a high camber for the canard and an airfoil with some amount less camber for the main wing. Airfoil selection is critical in canard design. If you get this wrong, you can easily end up with an unstable design from the start or one that deep stalls. Like we've covered, the canard needs to stall or hit its CL max before the main wing does. We can achieve this in quick 2D design stages by increasing the canard's airfoil camber. Remember that as camber increases, the CL alpha curve shifts to the left, meaning that the zero lift alpha decreases. The CL max will increase, but also shift to the left by some amount. We actually want both of these things, but we want them also on the scale of the wing, not just at the airfoil level. So don't forget that the airfoil characteristics are not exactly definitive of how your final 3D wing will perform, they're just indicative. Now you can see in this figure how increasing the camber fulfills both of our airfoil level requirements for the canard. Increasing camber makes the zero lift angle more negative, which is good because we're trying to get the canard to have a lower zero lift angle than the wing, and increasing the camber also shifts the CL max and therefore the stall angle to the left, which is also good because we want the canard to stall before the main wing. With that being said, we want to use a higher camber airfoil for canard than the main wing for decreasing the canard stall alpha and for decreasing the canard zero lift angle. Again, this is all 2D and considers no crossflow effects, no span-wise pressure distributions, no downwash effects. Therefore, this is just pointing us in the right direction for making our 3D design that much easier. Alright, so we keep saying that we need the canard to stall before the main wing. If you somehow miss this requirement when selecting your airfoils, using a high aspect ratio wing is another way to make this happen. As a reminder, aspect ratio is the ratio of the wingspan to the wing chord, or the square of the wingspan to the wing area. A straight high aspect ratio canard will be best. Remember that we want the canard to always be operating at the highest lift coefficient of all the surfaces on the plane at any given moment so that it'll reach its CL max sooner and stall before the main wing does, which would bring the nose back down to avoid a deep stall. if the Canard is operating at a high CL, it also will be operating at a high drag coefficient, and we really don't need to be adding any extra drag or laziness here. So the best bet is a nice and efficient high aspect Canard to optimize the lift distribution across it and decrease the induced drag as much as we possibly can, because after all, the lift induced drag increases with the square of the lift coefficient. You'll also see that most lifting Canard designs are built with really high aspect ratios because, as we just discussed, we want as efficient of lift as we can get up there, and that means minimizing our induced drag by optimizing the span-wise pressure distributions. We also know from potential flow theory that a high aspect ratio wing tends to have a more sudden or sharp stall compared to low aspect ratio wings, and this happens at lower angles of attack for higher aspect ratio wings. Quick aside on why this happens, because it's good to know. At the tip of the wing, the equalization of high pressure and low pressure below and above the wing respectively causes a local decrease in lift the closer you get to the tip. In a low aspect ratio wing, the pressure equalization effect near the wingtip is larger simply because more of the wing is closer to the tip. Therefore, a low aspect ratio wing needs a higher angle of attack to create the same lift as a high aspect ratio wing, because the high aspect ratio wing suffers less local lift loss from that pressure equalization out of the tip. Knowing that, it follows that for the same angles of attack, the pressure gradients over the low aspect ratio wing are more shallow than for the high aspect ratio wing, which generates more lift. And this means that separation requires a higher alpha to develop on low aspect ratio wings, and it will reach a higher angle of attack before stalling on a low aspect ratio wing. Remember that wings have 3D crossflow effects, and 2D airfoil characteristics and stall performances do not completely dictate wing characteristics. Also, since high aspect ratio wings have such a small decrease in lift at the tip, while the rest of the wing is an almost constant lift over the span, the wing is working harder, so the stall speed of a high aspect ratio wing will be lower than that of a low aspect ratio wing. For a really digestible explanation of why potential flow theory explains how higher aspect ratio wings stall at lower angles of attack, check out this link. Increasing the Canard aspect ratio doesn't just help with inducing an earlier stall onset. With higher aspect ratios, the downwash is decreased for the same lift. Remember, we're generating lift more efficiently with a higher aspect ratio. And weaker Canard downwashes will decrease the adverse effects on the main wing due to the Canard downwash skewing the actual alpha. Weaker downwash from the Canard results in a higher effective alpha of the main wing because we're adding a less negative downwash angle generated by the Canard. And like we've covered, the lower effective alpha of the main wing due to the Canard downwash means that the main wing produces less lift, which means that we either need to increase its incidence, its camber, or increase the wing area accordingly. General stall angle numbers are something like 10 to 12 degrees for high aspect ratio wings and 15 to 18 degrees for low aspect ratio wings. This channel is a one-man job. I tackle all of the research, all the editing, recording, CAD work, and CFD work behind the scenes. Juggling more than full-time aerospace engineering work, grad school, and finding the time during mostly super late nights to put these videos together takes way more caffeine than I'd like to admit. If any of my videos have helped your designs or curiosities make it from paper to flight, or maybe helped you study for the midterm tomorrow night that you've been ignoring, or maybe even taught you something new, a small coffee keeps the paywalls down so that I can keep this info accessible to everyone for free. Anyways, to those who already support me with their viewership, thank you so much for watching, commenting, sharing, and all the encouragement that you've given me. Before we go any further and discuss where we should place our canards on our design, we really need to understand the physics and aerodynamics taking effect here because it's complicated. Bear with me and don't shy away from the math. Thinking through this and repeating this process for your own design or layout makes you that much sharper of an engineer, a designer, a student, whoever you are. I'll save the time and let you pause the video to get oriented with this figure and the terms. Just an FYI, S refers to area, C bar refers to the mean aerodynamic chord, and the subscripts C and W here refer to canard and wing respectively. Taking a basic free body diagram for analysis, by definition, the canard is forward of the main wing, and so the quantity L sub W minus L sub C is positive. And naturally, the area and the chord length for both the wing and the canard are always positive. If neither the wing nor the canard have negative camber, then both moment coefficients and therefore the first two terms on the right-hand side of the equation must be less than or equal to 0. Since the lift on the main wing must be positive to support a major portion of the weight because we're flying, we see that the last term on the right-hand side of the equation must make a positive contribution to the lift. This requires that L sub c is less than 0, or in other words, the canard must always be mounted forward of the CG to maintain trim. Like I've mentioned, the aerodynamic interactions between the wing and the canard are super complex. The lift-induced tip vortex coming off the canard can interact with the main wing in a way that generates a flow too complex to evaluate with just simple calculations. And this really requires CFD or tunnel testing. So for now, we're going to neglect those effects and try to get in the ballpark of a representative system. If we solve for and differentiate the total pitching moment coefficient with respect to alpha, the CM terms go to 0 because they're taken about the aerodynamic centers of each wing. Remember that in the first video in the series about flying wing design, the pitching moment slope CM alpha must be negative for positive stability. I'm not going to spend the time explaining these right now, but if we take a couple of upwash correction factors and consider them in our differentiated pitching moment coefficient equation, we get this. So cleaning things up a bit and moving this equation to make more space, let's understand what this equation means. The first term on the right-hand side of this equation is the contribution of the wing towards the aircraft's pitching stability, and the second term is the canard's contribution. These terms are always positive, and remember that airfoil and wing lift curve slopes are also always positive. Now, we just derived that the canard distance to the CG, L sub c, has to be negative, so this means that in the equation that we're trying to get less than 0, the wing term is helping us because it's negative, but the canard term is hurting us because it's positive. Therefore, a canard always has a destabilizing effect on the aircraft. That sounds weird, right? I mean, if a canard is going to decrease our stability and push us closer to instability, why even bother with it? Well, the answer here is in the same exact equation. Looking at the first term, or the negative contribution term, for angles of attack less than stall, the lift slopes are positive, and this requires that L sub w is greater than 0. This means that the aerodynamic center of the main wing must always be aft of the CG for stable canard configurations. And you've probably already figured it out that it also must be far enough aft of the CG to counter the destabilizing effects of the wing camber, the fuselage, and the canard. Therefore, it is the main wing and not the canard that provides the stability for these configurations. If there were no tail, the main wing would cause the aircraft to pitch down because of the negative moment generated by the CP that's aft of the CG. So, while a traditional tail produces downforce behind the CG to counteract the negative pitching moment with a nose-up one, a canard will do the same thing by producing lift ahead of the CG. Since both the wing and the canard's pitching moment coefficients are typically less than or equal to 0, and knowing that L sub w must be positive, the lift on the canard must be positive. This is the advantage of the Canard design. Now, after rearranging the tail volume equations for angles of attack less than stall, we get this equation. And we've already covered that because the canard always must be lifting and supporting a portion of the aircraft weight, the canard should be designed with an aspect ratio as high as possible, just like the wing should be. Since the upwash gradient is positive ahead of the main wing, the first term on the right-hand side of the equation will usually be just less than 1. The second and third terms have small negative values because the wing and the canard have positive camber. Therefore, the wing lift coefficient over the canard lift coefficient ratio on the left must be less than some number that is less than 1. This means that the canard lift coefficient must be greater than the wing's lift coefficient to maintain both trim and static stability. This can be a bad thing if we're not careful, though. If our plane design requires a very high maximum lift coefficient for short takeoffs and short landings, there's no point of adding flaps to the main wing unless we add them to the canard as well. The entire aircraft's maximum lift coefficient will be controlled by the max lift coefficient of the canard. For this reason, it's going to be really rare to see canard configurations on an STOL aircraft. Now that we know the main design parameters that we need to pay attention to when laying out and sizing canards, we need to know where can we place them. Remember how important tail placement is when doing initial tail sizing calcs for a normal aircraft? The same importance applies here. And because canards are destabilizing surfaces, the canard effects end up being very sensitive to the vertical and horizontal positioning of the canard relative to the wing. The longer of a lever arm we have, the more pitching authority the lifting canard has, and the closer the lifting canard is to the main wing of the CG, the less of a role in pitching authority it will play. Now, this one should be obvious because we talked about it a couple minutes ago, but the shorter the distance between the canard and the main wing, the stronger the individual flow field interaction effects between the wake of the canard and the wing will be. In 1975, MIT published a paper titled Trim Drag in the Light of Monk's Stagger Theorem. Monk's Stagger Theorem states that the induced drag of a multiplane configuration is independent of the streamwise position or stagger of its lifting elements. This is valid for both monoplane tailplanes, aka conventional planes, and monoplane foreplanes, aka canard planes. Either of these two configurations can be regarded as a biplane element of zero gap, meaning that the vertical offset between the two elements is zero, and the trim drag due to the tailplane download or foreplane upload can then be easily calculated. Interesting enough, the trim drag penalty for both configurations is the same. Also, with the math, it ends up that the trim penalty disappears for tailplane or foreplane spans that are equal to the wingspan, like a tandem wing configuration. In this paper, the author shows that the cross-induced drag of the forward wing of a biplane is reduced by the upwash about it due to the aft wing, and alternatively, the cross-induced drag of the aft wing is increased by the downwash about it due to the forward wing. And remember, induced drag decreases with airspeed and increases with angle of attack as a fundamental result of lifting line theory. In fact, in a paper titled The Effect of Downwash on the Induced Drag of Canard Wing Combinations, published by the Royal Aircraft Establishment in 1981, we learned that the total induced drag of a multiplane system is unaltered if any of the lifting surfaces are moved parallel to the direction of motion, aka fore and aft. But this theory still rests on the assumption that the lift distribution on each surface is purely elliptical under the influence of the downwash field of the other, and it's clear that in order to satisfy such a condition, a lift-dependent twist needs to be imparted to one or both surfaces. Now, this is great to know for drag purposes, but what about lift and what about the pitching stability? I mean, after all, we're moving the tail to the front of the plane, so the moment arm of that placement from the CG will determine how much pitching authority a canard may have, and therefore change the respective stability derivatives. So we know from intuition that the canard will place the main wing in its downwash or a flow field that's directly manipulated by its downwash. So is it better to have the canard higher than, lower than, or in plane with the main wing? The answer is it's complicated. The higher the angle of attack, the more significant of an effect the canard vertical placement has on the main wing's lift coefficient. In a NASA study with a canard config delta wing, they found that they could squeeze out another 250 counts of the main wing's lift coefficient at high alphas when the canard was raised from below the main wing plane to above the main wing plane. With the canard in the low position, the lift increment per alpha is only a slight increase from a no canard configuration. NASA also noted a favorable wing-on canard interference, which was attributed to the upwash of the wing, which increases the effective angle of attack of the canard when the canard was in or just above the wing plane. In certain cases, a high but closely coupled canard will bend its trailing edge vortex down onto the wing, energizing the boundary layer and delaying wing stall by several degrees while stalling itself first. This is exactly what I mentioned earlier about the low pressure zone above the wing leading edge generated by the close coupled canard. This is also known as vortex lift, and the phenomenon does not occur with a low mounted canard. The configuration with the canard in the low or mid-plane position will see a significant increase in pitching stability at the higher lift coefficients, whereas the configuration with the high canard position will develop a nose-up pitching moment as alpha increases. Some research has also shown that the mid to high mounted canard on the same aircraft can reduce the total drag by anywhere up to 17% compared to the low mounted case, but I don't necessarily trust this paper, so you can read it for yourself. The major consideration in the vertical placement of a canard is the pilot's view. A low-mounted, slender canard will rarely obstruct the pilot's view, and this can also make it a little bit easier to mount pitot systems or different sensors on the nose. A high-mounted canard can easily block the pilot's view if not placed correctly, and it also makes the structural design and layout of the cockpit more difficult. So, quick design takeaways. High and close coupled canard placement is chosen when maximum trimmed lift, wing stall delay, and clean elevator authority matter more than added structure and deep stall safeguards. Low to mid placement of a canard wins when lesser pitching stability, a simpler structure, or a clearer cockpit forward visibility are the top priorities. Modern CFD and wind tunnel studies let designers tune the exact height to balance these trade-offs, and this often ends up showing the canard as optimal just above the wing chord plane where the vortex still re-energizes the wing without causing troublesome pitch-up issues. Before we wrap things up, let's talk about CG location. In a conventional wing and tail layout, the forward CG limit is usually determined by the ability of the tail to raise the nose wheel for liftoff. The limitation for VTOL configs usually involves the maximum percentage of the elevator that the designer is comfortable with dedicating to reacting the nose down moment caused by the forward CG placement. And in both, the aft CG limit is usually slightly ahead of the neutral point as to not diverge from stable flight. For a canard configuration, the forward CG location limit could remain the same if a similar tail area and moment arm are used for the canard. However, since the canard is always lifting, the canard effectively moves the center of lift forward and considerably reduces the CG range for stability. Considering geometric constraints, the practical CG range will usually be located from just ahead of the main wing's leading edge. Remember that when going through the free body diagram analysis, we determined that the canard has a destabilizing effect on the pitching stability. If we want to reduce this effect, we would want a low lift curve slope and to be considerate of the increased induced drag of the heavily loaded small wing. Quickly on the topic of canard span, figure 12 of this paper shows the results for the canard configuration of two regular wings having different span ratios. In the plot on the middle, the x-axis is the span ratio, or the canard span over the wingspan. The total lift of the canard arrangement is equal to the sum of the lifts from each wing in isolation only at a value of span ratio of 0.35. Below this, the loss in lift of the inboard of the main wing is more than compensated for by the gain in lift on the outboard portion of the wing. But again, this is all one big balancing act, and increasing the canard span will move the aerodynamic center forward, which can decrease longitudinal stability, it can decrease deep stall resistance, and it might require moving the CG range forward a bit to maintain that pitching stability. To summarize, we use canards to reduce the loading on the main wing, increase stall safety, and increase maneuverability. There are two types of canards, and these are lifting canards and control canards. We'll recap the streamwise positioning and vertical placement of these in a minute. The operating theory behind canards is that the canard must stall before the main wing. The canard's CLmax must be less than the main wing's CLmax, and this could result in a larger wing being necessary as we're naturally generating less lift than we could squeeze out of the wing due to the canard stalling first. The lift on the canard must be positive, this one should be obvious. The canard must always be mounted in front of the CG to maintain trim. The important one, canards always have a destabilizing effect on the aircraft. The aerodynamic center of the main wing must lie aft of the CG for stability. That's because it is the main wing and not the canard that provides the stability for these configurations. Finally, the canard's lift coefficient must be greater than the main wing's lift coefficient. Moving on to airfoil selection, remember that there are two criteria that must be fulfilled when designing a canard plane. First, the canard must have a higher CLmax than the main wing, and second, the main wing needs to reach the zero lift angle sooner than the canard. And increasing the canard's airfoil camber achieves both of these. For the canard aspect ratio, we want as high of an aspect ratio as possible. This increases efficiency as we minimize the induced drag with an optimized spanwise lift distribution. Remember that induced drag is proportional to the square of the lift coefficient, and because we always want our canard to be at a higher CL than our main wing, induced drag is a major player. We also want a high aspect ratio because these wings stall sooner than low aspect ratio wings, and we want the canard stalling before the main wing. Using a higher aspect ratio for the canard also decreases the downwash that affects the main wing's lift generation adversely. Just remember that after all of the positives that canards bring, they are ultimately often less efficient than conventional tails due to several factors, and one of which that is particularly important is the effect of the canard downwash. For the sake of time, I'll just put this recap on the screen as text, and I won't talk your ear off repeating this all again. If you want to pause it, go ahead. Anyways, here are some of the sources for the information presented here, and I'll toss some more sources in the description as well. I hope that what I've covered in this video can equip you as an engineer or a designer or a student, whatever you may be, and ultimately I hope that you've learned something and taken away something from this video. My comments are always open. I'm always looking for discussions. Thanks again for following along in the series, and I'll see you in the next video.